Hello, if you're out there waiting. I'm just waiting to make sure this is going live. Okay, here we are. Good morning, everyone. This is Jessica Allen, and I'm an ESD consultant with SUHO Australia. I work from our Adelaide office, and my main job is air tightness testing and thermography analysis. I'm doing a webinar today on thermography, so I'll be talking a little bit about what we find when we go into houses and mostly houses with a thermal camera, what defects we find. It can be quite interesting. Just need to close that. All of our webinars, as you are probably aware, are eligible for Green Star CPD, informal CPD points. So if you would like a certificate of attendance, please email us info@suho.com.au and we can give you that certificate so that you can claim your points. It would be great if you could interact in the chat and ask some questions if you're here live. That way we know that you were here during the webinar and can provide your certificate. So thermal imaging, a definition of thermal imaging is that thermal imaging cameras translate thermal energy into visible colours, which enable us to analyse surroundings. So they show very clearly temperature differences, and they can also sometimes show reflectance. So highly reflective surfaces do show up as different colours, which can be a little bit deceiving. So it's important that you understand what you're looking at when you use a thermal camera. But they're very good at picking up, obviously, temperature differences because they're thermal cameras, and they're quite accurate. They need about a 5-degree difference in temperature in order to work, minimum, preferably much more than that. If you have less than a 5-degree in an air tightness test situation, if you have air leakage coming through the gaps and cracks, and that air that's moving through is no more than 5 degrees warmer or cooler than the surface that it's moving across, you won't be able to pick up that air movement on a thermal camera. So ideally we've got more than a 5-degree temperature difference. The greater the temperature difference, the more visible the images are. Generally speaking, thermal imaging is used in a number of ways. It can be used in electrical work to find faults. It's used, as we are experiencing now during COVID-19, it's used for health purposes to detect temperature, body temperature. Police use it in their detective work, and of course it's used in thermal performance work. When I was doing this presentation, I did a little bit of Googling, and I found out that thermal imaging was first inspired by the sinking of the Titanic, because sailors wanted to be able to detect icebergs and other ships at a distance. And then the first camera was invented in 1929 for the British military to detect enemy aircraft. So thermal imaging has been around for quite a while. It is much easier to detect air movement when you're doing an air tightness test and you're using a thermal camera to detect air movement. It's much easier to detect that movement from inside a house. So this image here I've just grabbed off the internet to make the presentation pretty. This picture is of the outside of a building. This picture is not testing for air leakage, or at least I don't think it is. This is testing for surface temperature. So it's pretty tricky to find air leakage from the outside of a building using a thermal camera. Your best bet is to use, if you're trying to test from outside, using a smoke machine. Thermal imaging is much more useful if you are inside the building and can use those internal surfaces and the temperature difference inside to outside to create your pretty pictures. The things that we find during an air tightness test are air leakage, missing or damaged insulation, thermal bridging. They're the 3 most common ones that I find. Water ingress and electrical faults can also be picked up on a thermal camera. That's not really my job to look for those things. However, if I did find them, I would certainly let the client know. So here's a few examples of what air leakage looks like under negative pressure on a thermal camera. So negative pressure means that the fan in the door is sucking air out of the building, decreasing the pressure inside the dwelling or the building, which then sucks air in through all the gaps and cracks. So these images here, the purple splash marks that you can see, that's air being sucked in through gaps and cracks in the building fabric. All of these images were taken from the same house. So this particular house I tested a couple of years ago, but I use it as an example because it had a lot of air leakage that was really easy to fix. So the top left picture is behind an architrave, a window. The picture on the left is a thermal image. The picture on the right is the actual image. So you can see there that there is a lot of leakage coming from the top of that window, and generally what happens, I'm finding, and I'm hearing reports from a lot of people in the industry as well over time, is that builders, because they're usually restricted heavily on time and budget, they cut corners when they think nobody will notice. So up that high, that window is near the ceiling, they potentially would think nobody is going to ever look there to see if there's been silicone applied or if it's been painted, and they leave it. So these are the kinds of little defects that thermal imaging and air tightness testing pick up really easily. On the top right side, that is a downlight, an unsealed downlight. And this house had probably about 20 downlights in their living area, 16 or 20 downlights in their living area, and each one of them was unsealed. So they were all leaking like this. The purple marks that look a bit like paint has been splashed across the surface, that's air movement. So you can see that there's quite a bit of air movement coming through that downlight. And when you've got 16 or 20 of them just in one room, one downlight might not seem like a lot, but when you add them all together, that adds up to a very large hole in one room, leading directly into the roof space. The two bottom images are the top and bottom of the same window. So similar story here. You can just see the side of the window, there's no air coming through. So those two sides are going to be visible to the people living in the home. So the painters or the window installers have paid attention to the sides of the window. Bottom and top are a completely different story. No one's going to look there. It actually wasn't painted. I looked underneath that, it wasn't painted and it wasn't sealed properly. So thankfully, those sorts of window architrave leaks are really easy to fix with a little bit of silicone. Most homeowners, if they're a little bit handy, can figure out how to do that themselves. It's a low cost fix. And it's something that people don't normally think about when they think about why is my house so uncomfortable. You don't think about air leaking through the windows. So sometimes these things can be real eye openers. Here's some more examples of air leakage. That first house was about 10 years old. This house was actually built in a sustainable development up north, and it was meant to be 7.5 stars. 7.5 stars in 2010 is very different to 7.5 stars now. However, for its time, it was extremely ahead of the game. The person who, the modelling, energy modelling, had all the best intentions, and the design had all the best intentions. But when it comes down to how the building actually gets put together, you can see that there are a few defects in how that happened. And that means that this house is potentially not a 7.5 star house. It potentially performs much lower than that because the assumptions in the software and the heating and cooling loads in the software don't match up with what was built. These pictures, the top left is a new home, similar issue with the window architrave. The top right is an unsealed exhaust fan. That's just a fairly old, fairly standard exhaust fan in an existing home. Doesn't have a damper on it. So on the top of exhaust fans, there's like a closer that when the exhaust fan is on, it opens and the air exhausts out. And when the exhaust fan is turned off, gravity shuts the damper and stops air from moving in and out when the exhaust fan is off. A lot of them, especially in bathrooms, don't have these dampers because they're not required by the building code, especially in old houses. So they're not usually installed. But exhaust fan dampers, even though they're in unconditioned areas, have a fairly big impact on thermal comfort throughout the entire home because they're allowing a lot of air to move in and out continuously. Bottom left is a wall roof junction in a new house. You can see that there's some splash marks down the wall. So that is a joint that doesn't have a cornice on it. Just the air leakage is less about the materials that you use, and it's more about how you put them together. So when you think about, oh, is that material airtight? It's not necessarily about the air tightness of an individual material, it's how those materials are joined. So the junction between the wall and the ceiling in this instance wasn't perfect and was letting a little bit of air through. Similar story on the right hand side down the bottom. This was an older house. It's to be expected that these sorts of joins aren't going to be perfect in an older home. Not only were they probably not sealed at the time of building, they're also old and the house has moved and things have cracked and things. So that was another area of the junctions between the wall and the roof, the walls themselves, the corner junctions and the floor and the walls, those sorts of areas can sometimes be quite leaky as well. The other thing that we find is missing or damaged insulation, and this is quite common. All of these things are quite common actually. So the top left hand picture is a missing insulation batt. Both of the pictures on the left are both missing insulation batts. The one in the corner, I can't really explain what's going on and why that's not there. Maybe there was access issues. The builders couldn't get over into that corner, and so that bat is, or half of a bat is just simply missing. Or maybe they ran out of insulation or something, I'm not really sure. But that quite obviously shows that there is a big temperature difference there, which means that there is no insulation in that corner. The bottom picture is where insulation batts have been cut out around downlights. So downlights, depending on which downlight you use, some of them you can put insulation over the top in the roof space and others you can't because they get too hot. In this instance, it looks like these downlights, you can't put insulation over the top of them, and the clearance is generally required to be about 150 millimetres around each downlight to protect the insulation from getting too hot and catching on fire. But it takes time to cut a perfect circle out of insulation. So what trades usually would do is they just cut the bat in half, make it easy for themselves, and they just cut out half an insulation bat around each downlight, which is in excess of what is required, and creating a heat leakage pathway straight through the plasterboard, because heat just takes the least path of resistance straight up. And when you've got this much insulation missing, and similar to this client here, where they had 15, 20 downlights in their living room. I tested a house yesterday that had 34 downlights in their living kitchen area. If you've got insulation missing over every single one, that's a lot of heat you're losing through your ceiling. This top right picture is not a missing insulation bat. This one is just not fully in contact with the ceiling. So when it was installed, it got sort of squished in there a little bit, and it's not laying flat. Not as much of a problem as this situation, but it still is not a continuous insulation barrier across the ceiling, and you won't be getting the full effect of the R value in your insulation if you have it bunched up like that. So it's important that it's laid flat. This picture here, you can see that in this instance, there's still a little bit of plasterboard missing off the wall. So we got to this project just after that plasterboard had been put on the wall, and identified that there was a whole bat of insulation had been missed out of the wall completely. I think there was an electrical box on the other side, but that insulation should have been there, and the builders were called back and had to remove the plasterboard and install the insulation. So that was luckily picked up before paint had gone on, finishes had gone on, and it was something that was easily fixable. But if I had come to this building after it was finished, which I often do, I don't generally test buildings before they're finished. Ideally, we come in at an interim stage. In this instance, we did come in at an interim stage, and found this. So the owners of the building were very grateful. Here is another example of bunched up insulation. So you can see this is some beautiful rock wall insulation that's been installed pretty well. You can see that it's fully intact, fully touching all of the timber work, the studs. But the thermal image tells a slightly different story. It shows that it's a little bit bunched and that it could be butted up against the studs a little bit better. So you can see from the actual image it is a tiny bit bunched. The more continuous your insulation, the better it will work. The other thing that thermal imaging identifies is thermal bridges. So a thermal bridge is when outdoor temperature is transferred directly indoors via the materials in a building. So the image on the left is a timber frame. You can see the orange is insulation, which is nice and warm, and the purple is the timber frame, which is slightly cold. So this is, a brick veneer home or a lightweight timber home. This is happening in all of those homes. It's fairly standard. It's not as bad though as the steel frame. So you can see the middle picture, that's a steel frame under thermal imaging. So that was a warm day. The steel frame was quite warm and it lights up like a Christmas tree. So steel frames have a lot of benefits. One of their drawbacks is that they are not good for the thermal performance of a home. And we don't model the type of frame in residential modelling. When we do energy assessments, we don't actually model whether it's a timber or a steel framed home. So that isn't taken into account in the star rating or the energy assessment. Aluminium framed windows are the non-thermally broken aluminium framed windows are very cold, generally speaking. The house I tested yesterday was in Aldgate and it was, I think, about 6 degrees outside, and every single frame in the house was icy cold. So there was a lot of cool coming from outside directly inside, and the client's fireplace and mechanical heating was fighting against a number of things, but that was one of them. So those are some basic things that we find when we go into a residential dwelling and depressurise it. We find leaks, we find missing insulation, and we find thermal bridging. Depends on, they can appear in different ways in different buildings, but those three things are generally present. Something else that we found having some fun with a thermal imaging camera a while back, we had an event and we were playing around with it with people who were walking past our stall, and we found that men's noses were always warm and women's noses were always cold. It gave us a bit of a giggle. So that's all I have for you today for air tightness testing and thermography. That's it for this week's webinars. Next week we've got Monday, Wednesday and Friday, Navigating ESD in Town Planning Part 2. I'll be doing a session on air tightness testing for Green Star, and our Hubble guru Marco will be talking about planning a new home using his amazing energy predictive software. So thank you for joining me. Anyone who is out there, I'm going to check the chat if there's any questions. No questions. So thank you again, and I will see you next time. Bye.